So we can see that, first of all, we would only have an error if there is a fourth order derivative of this function w. For example, if w is a cubic, we shouldn't have any error here, right? We would have no error here because for a cubic function, the fourth order derivative is 0 and all the remaining derivatives are 0. So if you have a cubic, you use this finite difference formula, you get exact answer. Great. Otherwise, you have an error that is primarily proportional to delta x squared, which is what we see for the exponential function over here, as we observed. So that's a general way of analyzing how much of an error you get. Right? So basically, going from the example to the analysis, we show that what we observe on this specific example is not just applicable to this particular function. It's actually applicable to all functions that you can expand into Taylor series analysis. All right? Make sense? So what cases does this not apply? So when would you not expect the error of the approximation to decrease as delta x squared? Huh? When you what? You are drawing something? Well, pardon? Yeah, when some of these derivatives in my analysis doesn't exist anymore, okay, then you don't have this analysis, the analysis doesn't hold anymore. So, for example, if you have a function that may be continuous and differentiable and second order differentiable and third order differentiable, but maybe the fourth order derivative doesn't exist, right? What functions would that be? A cubic spline, right? For example, if you apply this to a cubic spline, I mean, it doesn't really hold anymore, right? So things like that you have to be careful about. And yes?
What else happens if you use a different step size forward and backward?
Can you say again?
If you use a different step size delta x going forwards and backwards.
Good question. If I use a different step size going backwards and forward, so my I plus 1 would have a delta x plus, my I minus 1 would have a delta x minus. Do you see anything weird about this analysis? What would be the leading term then? Well, the zeroth order term still cancels, but the first order term no longer cancels, right? So what does that mean? What's the order of the approximation? It's not even order 1, right? So the first error term is going to be here. It's proportional to delta x, but then you divide it by delta x squared, so your error actually is going to increase as you refine your grid points. So that's not a proper scheme to use at all. And in fact, if you want to derive a scheme with non-uniform spacing, you can't just copy that scheme. You have to actually if you want the second order derivative, you have to take a weighted average between these 2 points, right? I mean, you can't just take the center location. It's going to be here. You have to take a weighted average so that you are actually exactly at the ith grid point, and compare that weighted average with WI. And then you start analyzing what order it is. It's not going to also be second order. It's just going to be a first order scheme. If you're curious, repeat the analysis yourself. You can use exactly the same procedure. It's just less things are going to cancel. All right, yes?
When you calculate the truncation error, how do you cancel those two terms? Aren't they different? So that's the Taylor series differential, so it's like x equals 0, and then the other one is like x equals 9.
How did I cancel which term?
For the truncation error?
Like this term?
No, in the truncation error.
Here,
Yeah.
how did I cancel this and this, are you saying?
Isn't the second order derivative taken at different values of x? Isn't that from a Taylor series it's taken at x equals 0 and then that's taken at xi?
Okay, the question is, are these derivatives at different points, right? The answer is they are exactly at the same point. Actually, you have to be very careful about this. You can easily commit error if you do Taylor series analysis at different points and you actually cancel out derivative at different points. So you have brought out a very good point. So here, what I want to is approximate the derivative at x equal to I delta x, right? Which my shorthand is xi. So for this Taylor series analysis, remember I wrote it as wxi plus delta x. That means if all of these are actually delta x, that means the derivative as well as the function values are all at xi. If I expand all of these at 0, then this actually I have to replace the zeroth term by w at 0. I have to replace delta x by xi plus delta x, right? So my Taylor series expansion is actually at xi. And you have a choice on that. As I said on Monday, if you choose the point of the Taylor series expansion, instead of at xi, you choose it at xi minus 1. The same analysis actually goes through. It's just you have, when you are expanding at xi plus 1, for example, you will be dealing with 2 delta x as opposed to delta x. So the algebra is a lot more complicated, but like you get the same result, okay? You also have to expand this because this is at xi. You also have to expand this into Taylor series analysis, so it'll be more complex. Yes.
And you just dropped the big O terms because delta x cubed would go to 0 faster than delta x, right?
Yes. Yes. Right. So I dropped the delta, the big O term, but like I actually have to. I mean, to do the analysis properly, if you write a paper, your paper has to be accepted. You have to actually write O delta x fifth onto this, and you carry over, right, and show that the remaining term actually decays faster than this term. All right. Questions on this? No? All good? Okay.